Perfect. And we start off with a review of long division or a learning of long division if you never learned it in elementary school or middle school. And since some of you have never learned it in elementary school or middle school, it looks something like this. Okay? We're going to divide 2,748 divided by 13 without our calculator. The way that we do that with long division is we hit the computer button so that it's showing up in the right. It's not happy right now. I hit a really good button. Here we go. Here we go. This is not good. It's supposed to go all the way to the edge. And for whatever reason, it's not. So, we will just work with it. So with long division, you make a symbol that's kind of like a square root sign, but not a square root sign because it doesn't have a little hook thing there. And you write 2748 and the 13 outside. And the way that long division works is you look and say, is there any 13s in 2? No. But are there any 13s in 27? Yes. How many 13s could you get out of 27? You get one. You could get 2 of them, right? So what we do is above the 27, we write a 2. And we say 2 times 13 is 26. Now, technically, what you've done by writing the 2 above the 7 is that's really 200. Because it's written in the hundredths part. And technically, 200 times 13 is 2600. So we would know that our number, when we divide this by 13, it's going to be 200 and something. Well, if you did 200 times 13, that would take up 2600. And if we subtracted, you'd be left with 148. So now we go, oh, there's 148 left. Again, are there any 13s in 1? No, but are there any 13s in 14? Yes, there's 1. And we put the 1 above the tens column because technically that 1 represents 10. Now 1 times 13 is 13, but if it was a 10, it'd be 130. If we subtracted, we would be left with 15. And now we look, okay, are there any 13s in 15? Yes, there's 1, which 1 times 13 is 13, and that's just in your ones column. And you subtract. And we call what's left at the end the remainder. We have a remainder of 2. Did I?
Isn't 148 minus 130? 18? Yeah, would it be 18?
Yeah, that's 18. Oh, smoke. Thank you for noticing that great math. Look at that. What a save. Oh, yeah. That looks like. So it has a remainder of 5. So 2,748 divided by 13 is 211 with 5 left over. And what it means is if you took 211 and multiplied it by 13, you would get 2,743. You would have to add 5 more to make 2,748. So what long division does is it's a method of breaking things down so that you can add it up. Okay? Now, there are more than one technique. Some teachers teach long division in different techniques. So, for example, sometimes, let's see, what would be some other, sometimes I've seen a technique where you just draw a straight line. I don't know if anybody learned this technique. And then you have 2,748. And they say, well, if I took 100 13s, that'd be 1,300, and then I'd be left with 2,448. Oh, I could take another 100 13s, and now I'd be left with, wait, oh, wait for it. Want this to be a 1. Here we go. Wow. Take 100 13s, and I'd be left with 1,448. I take another 100 13s, then I'd be left with 148. I take 10 13s, then I'd be left with 18. I take one more 13, and then I'd be left with 5. I add up this side, it's 211, remainder 5. It's a different technique. But the long division technique is what we're going to be using something similar in this unit. So let's do the 4,212 together. So we started off 4,212 divided by 27. And again, you look, is there any 27s in 4? No. Are there any 27s in 42? Yes. There would be 1. And we write the 1 over the hundreds column, because 1 times 27 is 27, but we're really thinking 2,700. The one thing about long division when you learn it in elementary school or early in middle school is often you don't understand that that 1 really is 100. You just think it's a 1. And you're just copying down how you do it without understanding what it means. But if you had 100, well, that would account for 2,700. You would still be left with 1,512. And now you look, how many 27s in, oh, you'd have to go to 151 before you had a 27. A little bit of mental math here. Can you do 5? Can you do 6? What's 5 times 27? Yeah, you could, right? You can do 5, because 5 times 27 would be 135. That's really 50, so 1,350. Subtracting would leave me with 162. And then 6 of them works out perfectly to have a remainder of 0. So this tells us that 27 times 156 is perfectly 4,212. Now I'm color coding them for a reason, because I want you to see that what you did for the blue, you repeated that process and did it in green, repeated the process and did it in red. You're always looking at what are the first set of numbers and how many of that number could I get in. So if you had an easy, let's do one more easy long division. It's an easy long division. Because this number out here is just a 5. How many 5s in 8? 1. So I could put a 1 here, 5, that technically would be all of those zeros. And when we subtract, there you get that. Switch colors. Now, I look at my first numbers, and I have to go to 32. How many 5s in 32? 6. So I straight up from here, 6. 6 times 5 is 30. 0, 0, 0, 0. This technically, that's 60,000. And we subtract 2, 3, 6, 4, 1. Next number. I'd have to go to 23. How many 5s in 23? 4. 4 times 5 is 20. 0, 0, 0. And we subtract 3, 6, 4, 1. Next, I go to 36. How many 5s in 36? 7. 35, 0, 0. And can you see that we're just repeating the same process over and over again? How many 5s in 14? 2. 2. That'll give me 10. Subtract. And I'm going to get 41. And how many 5s in 41? 8. Leaves me 40. Leaves me 1 left over. There's no 5s left and 1. That becomes our remainder. And you could keep going. If you wanted, you could put a decimal there. And have decimal 0. And keep going until you hit finish. Or, if you're really good with your fraction, the remainder of 1 still needs to be divided by 5. 1/5 is 0.2. So if you wanted this exactly, it's going to be 164,728.2. And this is how long division works with numbers. What we are going to do is learn how to do long division with algebra. And it's the same process. So first of all, I'm just going to get you to watch the process. I have 3x squared minus 4x plus 5 divided by x minus 2. And just like before, I look at the first one. Is there something I could multiply x minus 2 by to get a 3x squared? I could multiply x minus 2 by 3x, because when I multiply this times this, I would get 3x squared. I'd also get minus 6x. Can you see how when I multiply the 3x times the x minus 2, this is what I would get? I'd have to distribute. And then what did we do with numbers? We subtracted next. We do the same thing in algebra, but I'll put it in brackets. Because I do this minus this, this will always work out to be 0, which is what we want. And then minus 4 minus a negative 6 would be plus 2x. And then 5 minus nothing is still 5. And we repeat the process, so I switch colors. Now, my first term is a 2x. Is there something I can multiply x minus 2 by to get a 2x? A 2. Put that above my 1's column, my constant. 2 times x, sure enough, that's 2x. And 2 times negative 2, that's minus 4. Put it in brackets and subtract. Now, we didn't have to put brackets around our numbers because there wasn't a worry about subtracting more than one thing. But with algebra, we do. Of course, that's 0 and 5 minus a negative 4 plus 9. That's your remainder. And what we figured out is that if you took x minus 2 and multiplied it by 3x plus 2, it would not quite work out. But if you added a remainder of 9, it would perfectly work out to 3x squared minus 4x plus 5. Basically, what we're finding out when we divide is what would work for everything except for the last number. Like check your first ones. Do you see that your first ones would give you 3x squared? Can you see that the outside and the inside would give you minus 4x? But the last ones give me minus 4, and I wanted 5. I would have to add 9 to get to 5. That's where the remainder shows up. So let's do one more together. Ooh, it's cubed. So it's going to be a little bit longer. We have 2x cubed minus x squared minus 2x plus 1 divided by x plus 1. Is there something, we look at our first term, is it 2x cubed? Is there something you can multiply x plus 1 by to get a 2x cubed? 2x squared. We would write that above your x squared column. 2x squared times x, sure enough, that's 2x cubed, and 2x squared times a plus 1 is plus 2x squared. Put it in brackets and subtract. This will be 0. Negative minus 2 will be minus 3x squared. And then the other ones will just come down because you're subtracting. Negative 2x minus nothing. 1 minus nothing would still be 1. Switch colors. Now my first term is a minus 3x squared. Is there something I can multiply x plus 1 by to get a minus 3x squared? Negative 3x. Negative 3x times x is negative 3x squared. Negative 3x times 1 is negative 3x. Put it in brackets and subtract. This will be 0. Negative 2 minus a negative will be plus x. And 1 minus 0 plus 1. Then, switch colors. Now my first term is an x. Is there something I can multiply x plus 1 by to get an x? 1. Plus 1. I get x plus 1, which I put in brackets and I subtract. X minus x is 0. 1 minus 1 is 0. We have no remainder. And this is a little foreshadowing of what is going to happen in this unit. If I write out what this means that x plus 1 times by 2x squared minus 3x plus 1 is equal to 2x cubed minus x squared minus 2x plus 1. What is this called? What's the math word for writing something like this? Factoring. Have you ever been able to factor an x cubed before? No. But we will in this unit. So this unit is more advanced factoring. In fact, once I get this 2x squared, I can use my old factoring techniques and factor it completely. So we will be able to factor more complicated things than we've ever factored before with long division. But that only works if the remainder is 0. This one didn't factor nice, right? Or at least we know that these aren't real factors because we have a remainder of plus 9. So this is called long division for algebra. And it's going to be helpful for figuring out how to write and factor things. But we're not having to factor until like tomorrow. So today we're not factoring. You didn't see that. Okay? So on the next page, they've got an example. They say, if you had x squared plus 2x plus 1 and you're dividing by x minus 1, you'd write out your long division statement. You would figure out, right, what times x gives me x squared? It would have to be x. You multiply that x by the x minus 1, then subtract. Then the next thing, oh, that 5 should come down. Then you'd say, now I have a new one. My new one is 3x. What times x would give me 3x? A plus 3. Multiply again, subtract again, and you get your remainder. Some words we call the answer, the quotient, and we call the remainder the remainder. The number that's left over is the remainder. Okay. So, something that never happened in numbers, okay? In fact, they have this here at the bottom. Two important rules. One, we always want to write in descending order. So if you have x squared plus 2x plus 5, you don't want to write x squared plus 5 plus 2x. You want to have, we would say the x squared has a degree of 2, the x has a degree of 1, 5 is a constant, has a degree of 0. Degree is its exponent. And you would have learned that word way back in grade 9 and subsequently forgot that word. So when we talk about the degree of something, we're talking about its exponent. So you always have to write in descending order of degree. This never happened in numbers. Because if you had 125, you would never decide to write the 5 in the middle and say, I have 125. Your teachers would say, okay, we need to get some testing because something is going wrong if you're writing 152 and calling it 125 because you're mixing your numbers up. But in algebra, it's allowed to mix them up because it means the same thing. So we have to make sure that we write it in the right order because we kind of have place value just like with numbers. The other thing that happens in numbers, that happens here, is we will need to include zeros when degrees are missing. Now, x squared plus 5 is the same as x squared plus 0x's plus 5. But we would never write that 0x. But we're going to need to for long division because we need a placeholder. You never forget zeros in numbers, right? If you have 1,032, you have to write that 0 in there. It doesn't mean the same thing if you just leave it blank or don't write the 0. So in numbers, we don't have to worry about these things because we do it naturally. But in algebra, in order for long division to work, we need to make sure the order is right and you have zeros when things are missing. So here's our first example. Seriously? We want to divide 2x cubed plus 5 minus 2x plus 3x squared by x minus 1. Can you see that we have to make sure we do rule number 1? It is not in the right order. The biggest degree is 2x cubed. Do we have any x squared? Yes, 3x squared. Do we have any x's? Minus 2x's, and then plus 5. And we're dividing by x minus 1. We didn't have to add any zeros because every degree was included. Then, is there anything you can multiply an x by to get 2x cubed? 2x squared. And 2x squared times this is 2x cubed minus 2x squared. Brackets around it and subtract. number one thing you will make a mistake in is in subtracting. Try to do it too quick and you might write x squared here, but it's 3 minus a negative. Come plus 5, and minus 2x plus 5. You don't have to write this 0 there, but you can if you want to, because they're going to subtract and go away. Then we switch colors. Now, I have a 5x squared. Is there anything I can multiply x minus 1 by to get 5x squared? 5x. And at this point, you're starting to feel good about this unit because you're like, yeah, this is not that bad. 5x times x is 5x squared. 5x times a minus 1 minus 5x. Bracket, subtract. 0, 2 minus a negative 5 would be plus 3. And 5 minus 0 would be plus 5. And the last color, we have a 3x. Plus 3. 3 times x is 3x. 3 times minus 1 minus 3. And I will tell you that most often where you will make your mental math mistake is in the very last one. You get so excited about finishing, you just do 5 minus 3. It's 5 minus a negative 3. It's going to be 8. Did any of you write 2? Or 1? Yes. I'm going to say that's where you're so excited about being done. The remainder is 8. And so now we know that if I multiplied x minus 1 times this, I would get this very close, except for the last number. I'd have to add 8 to make it work. It doesn't work out perfectly. So this tells me that x minus 1 is not a factor, because it has a remainder. But if there was a remainder of 0, then we would know it is a factor. All right, I'm going to get you to circle a couple of questions here, and then we will do example 2. So circle questions 3 ACE.